All right, so we're going to look at, this chapter talks about charge to start with, and then it talks about the forces between charges and so on. So we're going to start out with just a problem about charge. So this is going to be chapter 20, number 4. All right, so in chapter 20, problem number 4, it says a housefly walking across a surface may develop a significant electric charge through the process similar to frictional charging. Suppose a fly picks up a charge of 50 plus 52 picocoulombs. So you're going to have to remember what pico means. How many electrons does it lose to the surface that it's walking on? Okay, so Q total that the housefly picks up is plus 52 picocoulombs. Now the plus tells you that it's losing electrons, because the only way something can acquire a positive charge is for it to give up electrons. Then we have to get rid of this pico, all right? Pico, if you go back, if you don't remember what pico is, there's a chart, I believe it's in the front cover of your book, that tells you common prefixes, okay? In the front cover of your book, it's going to tell you that pico equals 10 to the negative 12th. Okay, so 52 picocoulombs is 52 times 10 to the negative 12 coulombs. All right, so I want to know how many electrons I lose to gain this charge. So I know that the charge of one electron, which is our unit charge, okay, the magnitude of the charge of one electron is 1.6 times 10 to the negative 19 coulombs. All right. I know the total charge, so the number of electrons then is pretty simple. You just take the total charge that you have and you divide by the unit charge. So the charge of one electron. So that's just 52 times 10 to the negative 12 coulombs divided by 1.6 times 10 to the minus 19 coulombs. The coulombs will cancel, and then you'll just divide those two numbers out and you'll get your answer. Okay, so I don't know what that is. I haven't worked it out, but you can figure it out if you want to. So it's going to be around something times 10 to the 7th electrons. So quite a few electrons, all right? So, but the thing here to remember is the unit charge is the charge of one electron, and that's always the smallest value of charge under normal circumstances that we'll have. We'll never have a charge that's smaller than 1.6 times 10 to the minus 19 coulombs, because electrons are what carry the charge. So they're the unit charge that moves things around. So you can't ever split an electron in half. So that everything's going to be a multiple of some of this number, the total charges are. Okay, all righty, so that is problem number 4. So now let's move on and talk about Coulomb's law. So in the notes, I go through developing how Coulomb's law came about and how you find the force between two charges. All right, so we'll start with problem number 14. Okay, problem 14 says a small plastic sphere with a charge of -5 nanocoulombs is near another small plastic sphere with a charge of -12 nanocoulombs. Okay, it says if the spheres repel one another with a force of magnitude 8.2 times 10 to the negative 4 newtons, what is the distance between the spheres? Okay, so what I've got is I've got two spheres that are negatively charged. They're a distance r apart. I'm going to call this one Q1, and I'm going to call this one Q2. Doesn't matter which one you call 1 and 2. It doesn't really matter. Okay, all right. Then it says they repel with a force of 8.2 times 10 to the negative 4. Now, even if they didn't tell me that they repel, I would know that they repel because these are like charges. So they repel because they are like charges. They're both negative. They're both negative, so I know that they're going to repel each other, even if the problem didn't tell me that. Okay, now they tell me the two charges, so I'll write those down. So I've got Q1 is -5 nanocoulombs. I don't like nano, so I'm just going to go ahead and get rid of that right now. 10 to the -9. Okay. And then I'm going to do the second one, which is -12 nanocoulombs. Again, I don't like nano, so I'm just going to go right ahead and get rid of that and leave it as coulombs. I need to do that because my proportionality constant is in units of coulombs, so I've got to get rid of the prefixes. So anytime I see a prefix on my coulombs, I might as well just go ahead and get rid of it because I can't do any math with a prefix on there. Okay. All right, then they tell me that the force between them, the magnitude of the force, is 8.2 times 10 to the -4 newtons. Okay? All right, so they want me to find the separation. Okay, so this is pretty straightforward. I've got the Coulomb's law of force equation in the notes, and it says the magnitude of the force between 1 and 2 is just K, that proportionality constant that I can look up, the magnitude of Q1 times the magnitude of Q2 divided by the distance between them squared. That's it. Okay. This is what I'm looking for. So let me just isolate that. Let me just go ahead and do a little bit of algebra. You couldn't wait to get, you couldn't get that drink before class started, huh? All right, so K, magnitude of Q1, magnitude of Q2, and then I'm going to move the F over like that. And I know all that stuff, okay? I know all that stuff. I know what Q1 is. I know what Q2 is. K, remember, is a constant that's given in the notes, or it's given in the book. K is 8.99 times 10 to the 9th Newton meter squared per coulomb squared. That's just a constant that's given by in the book. Okay, so that's like the universal gravitational constant. So all I need to do is plug in all my numbers. I know K, I know Q1, I know Q2, and I know F. So this is pretty straightforward. Just plug in all my numbers and solve for R. I got to remember to take a square root because this is R squared. So after I get my number here, I've got to remember to take the square root to get my answer. But you can do that. Okay, so that's not too bad. All right, now the thing about the force is the force acts along the line joining these charges. So if I were going to draw this, the force on Q1 would point over this direction, and the force on Q2 would be repelled in that direction, and Q1 would be repelled in that direction. So all the negative tells me, the two negatives tell me, is that they are repelling each other. I don't need to put those in the equation because the magnitude of the force only depends on the absolute value. The direction depends on the signs. So when I'm working a problem with force, I don't use the sign of the charge in the actual mathematical calculation. I just use it to draw my picture correctly. Okay, we'll see that again in a problem very shortly. Okay, so there's that one. Okay, so now we're going to move on and look at a slightly more complicated problem. All right, so let's look at problem. Let's see, I want to move over into some of the extra problems. We'll move in and look at problem number, well, we'll do 55 first because it's a little bit easier. Okay, and then we'll come back and do 53 because that's where we're going to have to get into, these are two are about vector components. Okay, so 55, you've got a drawing there. You've got two different scenarios. but we're looking at the problem. There's the scenario that we're looking at is on the left one. It says figure 2055. It says, what is the force on the 1 nanocoulomb charge in figure 2055? Give your answer as a magnitude and direction. Now, you should remember from physics 1 that force has to have magnitude and direction because it's a vector. So even if the problem doesn't say to give those two things, it says force, unless it says just the magnitude of the force, you need to remember that you've got to include magnitude and direction to have a complete answer. Okay, so I'm going to draw my picture first. So what I've got in problem 55 is I've got an equilateral triangle. At the top, and I'm going to draw my picture great big so I can see what's going on, I've got a plus 1 nanocoulomb charge. Then I've got on each side of my triangle, I've got 2 positive charges, and these are both 2 nanocoulombs. So these are both 2 nanocoulombs. Okay, if I get all my picture in one screen here, probably not. I drew it a little too big. Okay, so this is an equilateral triangle. Each side is 1 centimeter. And because it's equilateral, it's also equiangular. So I know that these angles are all 60 degrees. Okay, now your book told you that, but you should know that an equilateral triangle, then the angles all have to be the same. And they have to add up to 180. That's, stuff you should remember from algebra or, math class that you had at some point in your life, hopefully. But if not, kind of review that stuff and remember. Okay, so I'm looking for the force on this one. Okay, now what I'm going to do is, this is just a drawing of what's in the book, but I'm going to think about which direction the force would act. So I know that the forces on number 1 are going to act along a line joining it to the other 2 charges. So I'm going to number these. I'm going to call this one Q1. I'm going to call this one Q2. And I'm going to call this one Q3. And you can number them however you want. It doesn't matter, but that's the way I'm going to do it. So 1, 2, and 3. Okay. Now, if I just look at 1 and 2, 1 and 2 are both positive charges. So they're like charges. So that means 1 is going to be repelled by 2. So I know that the force from 2 on number 1 is going to push it away. Okay, it's going to try to push it away. So it's going to act along the line joining these charges. So if I imagine that line extending off into space like that, that force is going to act like that. So this is the force on 1 by 2. It's going to push it away. Same thing for number 3. Number 3 is going to try to repel it because they're both, again, both positive charges. Now here's the deal. It doesn't matter how big they are. For right now, it doesn't matter how big they are. The direction is just determined by, are they both positive, are they both negative, or is one positive and one negative? That's all I'm doing right now. I don't care about how big the force is yet. I'll do that in a minute. But right now, I just need to know that 1 is also going to be repelled by 3. And it's going to act along a line joining these charges like that. Okay, so like that. All right, so that's going to be the direction. Now, what I'm going to do to make my life a little easier is I'm going to come down here and I'm going to draw just a free body diagram of charge number 1 so I can see what's going on. Okay, so there's Q1. I'm going to draw my little coordinate systems here. Okay, so there's X and Y, just like normal. And then I'm going to transfer F1 and 2 and F13 to that. Now, what I need to know are some angles. So if I imagine the x-axis right here, well, if I look at my picture, if this angle right here is 60 degrees, then this angle right here is 60 degrees because those are the same. This is a horizontal line and this is that same line off that triangle. So I know that angle right there is 60 degrees. Same thing on this side. This angle is also 60 degrees. So when I come down here to draw my picture, I'm going to have F F12 like that, and that's going to be 60 degrees. And I'm going to have F13 like that, and that's going to be 60 degrees. Okay. Now I'm done with physics 2. I'm done with the physics 2. Now I've got to go back and remember how to do physics 1. So I want to find the total force here. So I have to think about breaking these up into X and Y components. So I've got an F12X like that, and an F12Y like that. And I've got F13X like that, and F13Y like that. Okay, so I break those up into their X and Y components. Now what I'm going to do to find the total force is I'm going to remember what my picture looks like and come back to it if I need to. And I'm going to write out the X and Y components of that force. Okay, so if I remember from physics 1, F total X is equal to F12X plus F13X. Then if I go here and I look at my picture, well, F12X is going to be minus F12 cosine 60. If you don't remember how to do that, you need to go back and review your stuff from physics 1, because I'm not going to spend time doing that. You should have learned that in physics 1 class. But if you don't remember, go back to the beginning of your book and look at that stuff. So F12X is minus F12 cosine 60. I'm going to do the same thing with F13X, but it's to the right, so it's positive. So I've got plus F13 cosine 60. Okay. Now I do have to remember some physics 2 here, because what are these forces? They're the Coulomb's law forces. So I have to remember that new thing that I just learned about Coulomb's law. So I've got minus F12 is going to be K magnitude of Q1 magnitude of Q2 over R12 squared, and then that's still times the cosine of 60, plus F13 is going to be K magnitude of Q1 magnitude of Q3 over R13 squared times the cosine of 60. Okay, so I still have to remember that because these are each Coulomb's law forces, so I just plug in that formula. But I know the charges, I know the distance between them, my calculator knows the cosine of 60, and I know what K is, so I can find F total X. And you'll solve for that, okay? Now, I'm going to do the same thing for the Y direction. So I've got F total X first. I'm going to do the same thing for the Y direction. So I've got F total Y is going to be F12Y plus F13Y. Okay. And that's going to be equal to, now, if I look at my picture from 600 years ago, okay, these are both up. So these are both going to be positive. The Y component here is going to be times the sine of 60 because it's opposite the angle. So these are both positive. So when I come back here to my equation, I'm going to have plus, this is going to be positive. So F12 sine 60, okay, plus F13 sine 60. Okay, but then again, I know these are Coulomb's law forces, so I can plug those in. So that's K magnitude of Q1 magnitude of Q2 over R12 squared sine 60 plus K magnitude of Q1 magnitude of Q3 over R13 squared sine 60. And again, I know all that stuff. I know K, I know Q1 and 2 and 3. I know the distances. I know what the sine of 60 is, or my calculator does. So I add those up. And when I add those up, I get F total Y is some number. Okay, now I'm not done. That's the X and the Y components, but if you go back and remember how to do the component method, now I have to use Pythagoras. So F total, if I've got the X component and the Y component, is just equal to the square root of F total X squared plus F total Y squared. And then the direction is you come from tangent theta is equal to the absolute value of F total Y over F total X. Now I use absolute value because I do the reference angle or the included angle, which tells me the angle from the x-axis, either the positive or the negative x-axis. Okay. And then I say, okay, it's either to the right or the left or whatever. I do that myself. I don't try to do, I don't try to put in the signs here if one of these is negative, because my calculator doesn't know the difference between a first and a third quadrant angle and a second and a fourth quadrant angle. So I just draw the picture myself and figure out it's pointing to the left or the right or above the x-axis or below the x-axis. I say that myself instead of trying to let my calculator do it, because my calculator's stupid and it doesn't know. So I use the included angle here. Okay. All right, so this is a generic approach to this problem. Now, some of y'all have probably already spotted the fact that for this particular problem, the X components cancel out, okay? But that's not always true. So I wanted to work it in the most general way so that you would know that sometimes you just have to do it the hard way. You have to put all the numbers in and do all the math, okay? But it all starts with that free body diagram, just like you learned in Physics 1. So this is good old Physics 1 component method of vector addition using a free body diagram, okay? All righty. So that gets you one of those worked out. Let's do another one. Let's do, let's look at problem. Let's go back and look at some about electric field. So let's go back and look at problem 26. Okay. 26 says a 30 nanocoulomb charge experiences 0.035 newtons of electric force. What is the magnitude of the electric field at the position of this charge? Okay. So I know this is where I had to talk about my test charge and my source charge. Okay. So it's 30 nanocoulombs. So that's my test charge. That's the thing that I'm sticking in the electric field to experience the field. So I'm just going to go ahead right away and get rid of nano, make it 10 to the minus 9. And then I know the force is 0.035 newtons. Okay. So it wants me to find the magnitude of the electric field. I don't need to know the direction. I just need to know the magnitude. Okay. All right. So when I look at the notes, there is a formula in there that says the magnitude of the force of the electric field force is equal to the test charge times the magnitude of the electric field. Okay. So I need to find E. So E is just simply the magnitude of the force divided by the value of the test charge. So that's pretty straightforward. 0.035 newtons divided by 30 times 10 to the minus 9 coulombs. And that's pretty easy. Now it only wants the magnitude, okay? The thing that you'll learn in the notes or in the reading is the direction of the force on a charge depends not just on the direction depends on its charge in relationship to the magnetic field, okay? So if electric field. So if I have an electric field say somewhere that points to the right, okay? A positive charge will be experiencing a force in the same direction as the electric field. Because if I remember my reading, the electric field points away from positive charges and toward negative charges. So if you have a field pointing like this, that's created by something over here that has a positive charge. And if something over here has a positive charge, it's going to push a positive charge away from it. It's going to repel. So the positive charges, whatever size they are, always go with the field lines with their force. A negative charge, on the other hand, would be attracted to this positiveness over here, creating this field. So instead of going with the field lines, it actually goes opposite the field lines. So the force on a negative charge goes opposite the field lines. Okay, it doesn't matter how big it is, it's always going to go opposite the field line direction. Okay, so the force on a charge is a little different than gravity, because with gravity, everything was attractive. Everything tried to pull masses together. Here, the force is going to depend on the sign of the charge in relationship to the direction of the field. So positives will always go with the field. Negatives will always go opposite the electric field. Okay? All right. Here, they just asked for magnitude because we didn't know which direction the field was pointing. But if we know direction and we have a test charge, we can say we know which way the test charge will move. All right, let's do another one. Okay. All right, let's look at problem 29. Problem 29 says, what is the strength and direction of the electric field at the position indicated by the dot in figure 2029? Specify the direction as an angle above or below the horizontal. Okay, now here's the thing with electric field. It's a vector, just like force is a vector. So I can still use a free body diagram to analyze it. So let me just draw the picture that goes with the problem first. So what I've got is I've just got a coordinate system kind of set up here. Okay, well, that's terrible, but you can draw better than that. Okay, up here, I've got a +1 nanocoulomb charge. Down here, I've got a +1 nanocoulomb charge. This distance here is 5 centimeters. And this distance here is also 5 centimeters. And then over here somewhere, I have a point. I don't have to have a charge there to compute the field, because remember, the field is present all the time, whether or not there's a test charge there to feel it. So it turns out that this distance right here is also 5 centimeters. So they like 5 centimeters in this book, apparently. Okay, so I want to find the field at this point due to these two charges. Okay, so positive charges, their fields point outward. So if I imagine a line connecting these charges, and I'm going to call this one 2, and I'm going to call this one 1, and I turn the light off. Okay, I'm going to call this one 1 and this one 2. If I imagine a line joining these charges, what that means is the field would point along this line. So up here at the point that I'm interested in, that field's going to point up like that. So that's going to be E2. It's going to point away from the positive charge, and it's going to be along the line, connecting it to the point that I'm interested in. Okay. All right. Then over here, I've got the same thing going on. Okay. I've got a positive charge. I've got the line drawing them like that. And that's going to be E1. So there you go. Okay. Well, what I've got here is a triangle again, except it's not quite as simple as what I had before, because now I've got a right triangle. Both of those are right triangles. The distance between the charge and the point now is this distance. It's the hypotenuse of those little right triangles. So this is R1 and this is R2. So I'm going to have to do a little bit of trigonometry to figure that out. Okay. So what I've got for my R1s and R2s is a little triangle that looks like this, where this is 5 centimeters, this is 5 centimeters, and then this is R1 or R2. Now, again, I don't like centimeters, so I just need to go ahead and make those 0.05 meters before I do any math and mess myself up. But I can find this by using Pythagorean theorem again. That's just going to be 0.05 squared plus 0.05 squared. Take the square root. Okay? So you can find that R pretty easy. All right, so now electric field, though, is a vector. So it works just like when I have a force. I'm going to do the same thing. First thing I need to do is find some angles. Well, this is a isosceles right triangle. So if this is 90 degrees and these two are both the same length, then I know that angle there is 45 degrees and that angle there is 45 degrees. Okay, so what that means is if this angle is 45 degrees, this angle is 45 degrees because they're vertical angles or something like that from geometry. But I just know that that angle is 45 degrees. Same thing coming from this direction. This angle is going to be 45, so that angle is going to be 45. Okay, so once I know that, I can draw the equivalent of a free body diagram. I can draw a vector diagram for that point over there where I'm trying to find the electric field. So if I come down here and I do that, there's my point. I'm going to draw my coordinate system real quick. I've got E1 pointing up like that. I've got E2 pointing down like that. I know these are both 45. Or no, I've got those backwards. This is 1 and this is 2, excuse me. Got those backwards. All right. So they both point like that. I've got E2 points up, E1 points down. They're both at 45 degrees. Okay. So now I'm going to do a vector component problem for that point right there using my picture. Okay, so this is 29 continued. So I've got my 2 points. So I'm going to remember my picture here. I'm going to look at it and then say, okay, I've got an E2X and an E2Y that points up like that, and an E1X and an E1Y that points down like that. So I'm going to remember what my components look like. I'm going to do the same thing as I just did on the previous problem, except with electric field. So E total X is equal to E1X plus E2X. Okay, now if I look at the X component, both of these are going to point to the right, so they're both going to be positive. And also if I look at my picture, it's going to be cosine 45 for both of them. Okay, so I've got E1, it's positive, cosine 45, plus E2, cosine 45. Now, I have to remember what the formula for the electric field of a point charge is. That's given in your notes, okay? The electric field of a point charge, remember, is K, magnitude of Q, the source charge, over R squared. So it looks a lot like the Coulomb's force equation, but the test charge has canceled out. Okay, the test charge has gone away. So this is the electric field of a point charge. That's what I'm going to put in my equation. All right, so I'm going to come back over here, and I'm going to say K, magnitude of Q1 over the distance from charge 1 squared, which I figured out using my little triangle, times the cosine of 45, plus K, magnitude of Q2 over the distance to charge 2 squared times the cosine of 45. And I think I know all that stuff. Okay, I know all that stuff. So that's E total X. I'm going to do the same thing, but now I'm going to do it in the Y direction, E total Y. So it's going to be E1Y plus E2Y. Okay, I go back and I look at my picture. E2 is going to point up, E1 is going to point down. Now they're going to be opposite the 45-degree angle, so they're going to be sine of 45. So E1 points down, so I've got minus E1 sine 45 plus E2 sine 45. And I'm going to use that same expression to plug in for E1 and E2 because it's still the electric field magnitude. So it's going to be minus K magnitude of Q1 over the distance to charge 1 squared sine 45 plus K magnitude of Q2 over the distance to charge 2 squared sine 45. And I know all that, right? That gives me X and Y, but that's not, I'm not done. Okay, I'm not done. I have to use Pythagorean theorem again because I'm not done yet. So I've got X and Y. So I'm going to do the same thing I did before. E total is the square root of E total X squared plus E total Y squared, just like I did with the forces. And then the angle, tangent theta, is going to be the magnitude of E total Y, the Y component, divided by the X component. So just like I did with the forces, okay? If I look at my picture, oops, there it is. If I look at my picture, I can kind of tell which way it's going to point, all right? Again, these happen to be equal, so the Y component's going to probably cancel out here. That's not always going to be the case, so I approached it in a generic way, but it'll tell me the direction. I'm going to be with a positive X and some kind of a Y, so I'm either going to be above or below the horizontal, or if they actually exactly cancel out, it'll just be all in the horizontal direction, okay? But you're not done until you give me these two pieces of information. This is the complete answer here, the magnitude and the direction of the electric field, okay? Now, one thing that I didn't mention in the notes, the units of the electric field, if you go back and you look at the equation that we used in the previous problem, the units of the electric field can be expressed as newtons per coulomb. Okay, that's fine to give the unit in newtons per coulomb. We'll see it in other units when we get into other chapters, but for this unit or for this chapter, it's fine to express the electric field in newtons per coulomb. So what that does is that tells you how many newtons of force is on a single 1 coulomb charge. Okay. All right. All right. So that gives you sort of an overview of the different types of problems that you'll see in this section. This is the hardest test. I'm just going to tell you straight up. This test tends to give people the most difficulty simply because it has all of these components and all that stuff. And if you haven't already noticed, there's two formulas that look very similar. Field and force kind of look the same, right? They look like the same formula. So it gets people confused. So one of the things that happens on this test is you need to make sure you pay attention to the question. The question may ask you for field, and if you solve for force, I can't give you any points because you didn't solve for the correct thing. So both field and force are vectors, all right? They're both vectors. They're both dependent on the magnitude of the charge for the calculation, and then you just use the sign of the charge to figure out direction. So we don't use the sign of the charge in the calculation, all right? Force requires a test charge. Field does not. Field is around as long as there's a source. The force requires a test charge. So start kind of getting in your head the similarities and the differences between field and force. And I say that because in the next chapter, we're going to see potential and potential energy. And they look almost just like these formulas too. So there's 4 things that are all very different, but that look similar, and they get people confused. So one of the things that is a common stumbling block on this test is getting those things kind of separated out. So when you read a test question or you read a homework problem, be really careful to see what it says to solve for. Because if you solve for the wrong thing, I can't give you any points because you didn't do the question I asked. All right, so that's something to, to kind of commit to your memory or writing your notes as you're preparing yourself. Make sure you really distinguish the difference between those 4 quantities. They're all related too. They're all related to each other. I call them cousins because they're all related, but they're not close enough to be brothers and sisters. Okay, so they're all similar and they all give you information about what a charge is doing, but they're all very different. Okay, all right. So right now, does anybody have any questions that they need addressed? I'm going to go ahead and stop the recording.